Welcome back. Today I will discuss series. In my previous video, I have defined 3 lectures about series and I have defined more questions on series which had come in different type of competitive exam. Today I will discuss series as a review, and today I will prove some theorem of series as a just deep knowledge about series. Okay? Consider the series AN, which is infinite series associated with the sequence AN. We all of us know the partial sum of the sequence. Partial sum of the sequence is, just as a review, this S1 equal to A1, S2 equal to A1 plus A2, which A1 means S1, S3 equal to A1 plus A2 plus A3, and this is actually S2 plus A3, and Sn equal to A1 plus A2 up to An. This is the n partial sum of the series An. Sn be the sequence in R. If Sn converges to S in R, where S is the sum of the infinite series, then we can tell the series AN convergent. If the partial sum Sn is convergent, then we can tell the series AN is convergent. We all of us know this idea. This idea I have defined in my previous video, when a series convergent, when a series divergent. Actually, a series is convergent means partial sum of the sequence is convergent, and a series is divergent means partial sum of the sequence is divergent. And if the partial sum is such type, consider the sequence AN in R. If this is term be greater than equal to 0, then Sn equal to A1, A2 up to An. This is equal to actually Sn minus 1 plus n, and since each An greater than equal to 0, that means Sn minus 1 plus An, this is greater than equal to Sn. That means Sn is an increasing sequence. That means partial sum is an increasing sequence. We all of us know an increasing sequence be a convergent when the sequence is bounded above. That means since Sn is increasing, then if Sn is convergent, if the sequence is a partial sum of the sequence is bounded above, and then we can tell the series, the partial sum of the sequence Sn is convergent, then our goal is done. The series AN is convergent if we can show this part. When each term of the series is greater than 0, then this would be follow. Otherwise, these rules would be applicable when partial sum of the sequence convergent to a limit point, then we can tell the series is convergent. And when partial sum of the sequence does not convergent in the limit point, then the series does not convergent. I hope my all viewers have understood this concept easily. Actually, this concept and this type of question which had come in different competitive exam, I have defined in my previous video elaborately. Actually, today I will discuss this topic just as a review and also deep concept. For example, consider the series AN equal to 1 over n times n plus 1. That means here this series is generated by this sequence AN equal to 1 over n times n plus 1. And notice Here we have to prove is this series is convergent or divergent. One over n times n plus 1. We can write this as 1 over n minus 1 over n plus 1. Here we have to show is this partial sum is convergent or divergent. Notice S1 equal to 1 minus half and S2 equal to 1 minus half plus half minus 1/3. Similarly, this would be continue. Similarly, Sn equal to this would be and this would be cancel. After cancelling, Sn would be Sn equal to 1 minus 1 over n. Notice here Sn is increasing sequence and Sn less than equal to 1. Since Sn partial sum of the sequence is monotone increasing and bounded above, then obviously the series An is convergent series. Okay? This theorem has used. I hope my all viewers have understood this topic. Now consider the sequence An equal to r to the power n. And we all of us know when r less than 1, then this sequence tends to 0. Here we have to show for r greater than equal to 0 is the series An is convergent or divergent. We all of us know the partial sum Sn equal to 1 plus r plus this would be continue plus r to the power n. And this is equal to 1 minus r to the power n plus 1 over 1 minus r. And this is true when r not equal to 1. We all of us know this theorem, this formula. We have to show is Sn is convergent or divergent. When r equal to 1, then obviously Sn equal to n plus 1 and this is bounded sequence. So we can tell easily Sn does not convergent because this is the bounded sequence. Now I will say for r not equal to 1. When r not equal to 1, then Sn equal to 1 minus r to the power n plus 1 over r 1 minus r. We can write this as 1 over 1 minus r times 1 minus r to the power n plus 1. And this is equal to 1 over 1 minus r minus r to the power n plus 1 over 1 minus r. Notice 1 over 1 minus r, this is actually the constant term. Okay? And we all of us know constant series, consider this series as C, constant series, then constant series always convergent because if then the partial sum converges to this constant term, so obviously since limit exists, so obviously constant series always convergent. Now consider this constant series as a Bn and this is as a An, and here constant because here no term of n. So this is, now rewrite this series, this partial sum as Sn minus Bn equal to An. This part is convergent. Now we have to prove is An is convergent or not. Sorry, here not An, here minus An. Now An equal to r to the power n plus 1 over 1 minus r. We can write this as 1 over 1 minus r times r to the power n plus 1, and this is obviously constant sequence. This is r to the power n plus 1, and the sequence An is convergent if r to the power n minus 1 is convergent. And we all of us know the sequence r to the power n is convergent when 0 less than r less than equal to 1. And notice here I have considered r not equal to 1. That means this term is convergent when 0 less than equal to r less than 1. That means this term is convergent when r lies between 0 less than r less than 1. For this interval, n equal to r to the power n means this series with constructed by this sequence is convergent. Okay? That means the series n is convergent when partial sum of the sequence is convergent. And we all of us know a sequence is convergent, that imply this sequence always Cauchy. That means if the series is convergent, then partial sum of the sequence is convergent and this partial sum is Cauchy. And Cauchy means for all epsilon greater than 0, there exists capital N belongs to natural number such that m comma n greater than equal to capital N, absolute value of Sn minus Sm strictly less than epsilon. This is the definition of Cauchy, we all of us know. And this is true for all m comma n greater than equal to capital N. And if n greater than equal to m, then this implies absolute value of a1 up to am plus am plus 1 up to, this would be continue plus an. And here since Sm means minus a1 plus a2 up to am, and here n greater than equal to m. So since n greater than equal to m, that implies am plus 1 up to an strictly less than epsilon. Therefore, when a series is convergent, then that implies absolute value of am plus 1 plus an strictly less than epsilon. Okay? OA. Now let's consider the series 1 over n. We all of us know this series is divergent series. And today I will prove this series because I have told you many times, this lecture is actually for deep knowledge in series. So I have considered this example. We have to check the convergence of partial sum Sn equal to 1 over n. Notice S1 equal to 1, S2 equal to 1 plus half, S3 equal to 1 plus half plus 1/3, S4 equal to 1 plus half plus 1/3 plus 1 over 4. Similarly, Sn equal to this and S2n equal to this. And notice S2n minus Sn equal to 1 over n plus 1 up to plus 1 over 2n. Okay? And notice this whole term is greater than equal to 2n times n, because this is occur how many times? This is occur 2n times. So we can tell this S2n minus Sn strictly greater than equal to 1 over 2n times n. That means this is greater than equal to 1 over 2. So S2n minus Sn greater than equal to half. I hope my all viewers have understood this option, and this is true for all natural number. Okay. Therefore, if Sn is convergent, that implies, we all of us know, convergence sequence always imply this sequence is Cauchy sequence. But by this idea, S2n minus Sn greater than equal to half. This is true for all n. By this idea, this is not Cauchy. So Sn not Cauchy. That means since Sn not Cauchy, that imply Sn is a divergent sequence. And since Sn is divergent sequence, so the series 1 over n is divergent series. I hope my all viewers have understood this is clearly. Okay? Oh well. Now I will say one nice test. Comparison test. We all of us know comparison test. Also, in my previous video, I have discussed many questions based on this comparison test. Today, I will discuss this test just as a review. Also for higher study, also for deep knowledge in series. Okay? At first, just as a review, just recall what is the comparison test. What is the statement of the comparison test? Consider an bn be a sequence of non-negative real number. This is be the associated infinite series. Assume for all n greater than equal to capital N, an less than equal to bn. Okay? And comparison test is, the statement is, if the series bn is convergent, then that implies the series an is convergent. This is the statement of comparison test. Now I will prove this theorem. Consider a1, a2, an minus 1 up to a here small n, and b1, b2 up to bn minus 1 here small bn. Notice, since for all n greater than equal to capital N, since an less than equal to bn, therefore this condition is true since for all n greater than equal to n, capital N. Therefore, after capital N, this condition would be applicable. Okay? Then, is such type. Consider Sn be the n partial sum of the series A and Tn be the n partial sum of the series Bn. And for each n, an greater than equal to 0 and bn greater than equal to 0. And here given for n greater than equal to capital N, after capital N, an less than equal to bn. And in the statement, assume an bn is convergent. Then we have to prove an is convergent. So, assume bn is convergent, then we have to prove an is convergent. Is an less than equal to series bn, and this is true not for all n greater than equal to capital N. This is true all n belongs to natural number. Because just recall the definition of convergency. In convergency, definition of convergency, finite term does not matter. So, this is series an less than equal to series bn. This is true. This condition is true for each n. Since Sn be the n partial sum of an and Tn be the n partial of sum of bn, so obviously Sn equal to a1, a2 up to an, and since an less than equal to bn, that means this is obviously less than equal to b1, b2 up to bn, and b1, b2, bn means obviously Tn be the n partial sum of bn. Obviously this is less than equal to Tn. Therefore, for each n, Sn less than equal to Tn, where Sn is the n partial sum of n and Tn be the n partial sum of Bn. Assume series Bn is convergent and obviously Bn is greater than equal to 0. So their partial sum Tn would be always monotone increasing function. And since the series is convergent, that means this partial sum always would be bounded above. And that means since this is bounded above, that means Tn, this partial sum converges to T, where T is the LUB of the set Tn where n belongs to natural number. Therefore, for each n, Sn less than equal to Tn, and since Tn converges to T, where T is the limit of the sequence Tn, therefore this is obviously less than equal to T. Therefore, I have got for each n Sn less than equal to T. So, since Sn less than equal to T, that means obviously that imply Sn, the sequence Sn is bounded above. Sn is the partial sum of the sequence n always greater than equal to 0. That means since n greater than equal to 0, that imply this partial sum is monotone increasing. And since partial sum is monotone increasing and bounded above, that means this partial sum always convergent. And this convergent to, consider this is S. And S is nothing but, this is actually LUB of the set Sn where n belongs to natural number. Since Sn converges to S, that implies the series An is convergent series. I hope my all viewers have understood how the proof. Today I have proved this theorem just as a concept, just deep concept about series. Okay? In this video I will discuss various type of question. Also in my previous video I have discussed many questions based on this theorem. If you don't see my previous video, at first I will highly recommend you please see my previous video. Then today's video would be so comfortable. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.